In this video, we'll be looking at the liquid property known as viscosity. And the last physical property of liquids that we're going to discuss is viscosity. Viscosity is a liquid's resistance to flow, how little it wants to flow. So you've probably noticed the difference between water and honey. You can readily see that water flows very easily and honey does not, much slower. In this case, water has a low viscosity and honey has a high viscosity. Viscosity is dependent upon interparticle interactions. The more interparticle interactions there are, the higher the viscosity. Water has hydrogen bonding, but honey has even more hydrogen bonding. Sometimes 6, 8, 12 hydrogen bonds are holding it together. All those hydrogen bonds make the molecules stick together so they don't flow very easily. So now let's look at how viscosity is tested. It's basically you pour it out and you see which one goes the fastest and which goes the slowest. So this example shows some motor oils as they're pouring out. For this test, they have to use the same type of test tube. They have to use a flipper that allows it to all fall at the same time, and they have the same volume to start with so that the liquid goes the same distance. In this case, you should be able to see that the sample in the middle has the lowest viscosity because it's flowing the fastest, and the one on the right-hand side should have the highest viscosity because, as hopefully you can tell, it is the furthest behind, it is flowing the slowest. One of the main places that we look at viscosity is in motor oil. One thing that most people know about engine motors is that they start off cold, and as they continue to work, they'll get hotter and hotter. We also know that most liquids change their viscosity depending upon the temperature. For example, we can look at honey. This video shows the difference between hot and cold honey. We start here on the left-hand side with room temperature honey showing how slowly it will pour. And hopefully you can see that it has a very high viscosity. On the left, we're going to pour out the hot honey, and you can see how much lower the viscosity has gotten. It pours out very rapidly. And in this case, what we see is that we're weakening the bonds as they get hotter and hotter. Those intermolecular forces will start to weaken. So we start to see hydrogen bonding in particular being weakened by the warmth of the solution. A similar thing happens to oil, though, so that as the engine warms up, the oil becomes less viscous. So the logical thing then would be to use a very viscous oil. But it ends up that doesn't work either. So let's look at what happens when we add oil to our car and how it flows through the engine. So first, when you add the oil, you're going to pour it in, and it's going to go down to the bottom into a sump, basically a pool of oil at the very bottom of the engine. You see it at the bottom? And it takes about 12 seconds, but the pump starts to pump, and you'll start to see the oil rising up. It's going to go through the filter, has to clear the filter, and now it's going to go up onto the camshaft, some of the moving parts. You'll see the cams are going to get bearings and things like that. We'll start to get oil on them, and it's going to continue to rise up, and it's going to go up into the rocker heads and the pistons, and we'll see that it takes a total of 12 seconds to get everything lubricated. So why does this matter? Well, if you have a very viscous oil, this will not rise nearly as quickly, and of course that means that everything will be pumping without lubrication. And that's a big problem because that means that those metal parts are grinding against each other and wearing out and causing damage. Of course, if the oil is not viscous enough, it will start to coat those things, but it'll fall right back off, similar to the way water would wet something. It'll wet it initially, but then it won't be there to lubricate like we need it to do. So how do you get the right viscosity? The Society of Automotive Engineers, the SAE, has ranked various oils at different viscosities. And so they give something like a number like 10, 20, 30, 40, and that'll tell you what the viscosity is at that temperature range. So an SAE of 40 has a temperature range of around 10 degrees Celsius to 40 degrees Celsius, and in that temperature range, any oil that has an SAE of 40 should have that same viscosity of 40, while an SAE of 30 in that same temperature range of 10 degrees Celsius to 35 degrees Celsius will have an SAE of, but notice that the temperature range goes a little bit lower for the SAE of 30. It goes down between -5 degrees Celsius and 35 degrees Celsius. So each of these oils are ranked kind of in a temperature range, and we can see where they will fit. So if we go all the way to the top, we see SAE of 0W. That means 0, and that's a winter weight oil or a winter oil. And what that means is that we're looking at colder temperatures. So in this case, it's going below 10 degrees Celsius. And that's where we measure the SAE of 0W, is generally below 0, but in this case below 10 degrees Celsius. It will act like a 0 viscosity oil. So as you can see, any of the single weight or single grade oils have a problem with temperature. They either can't go to colder temperatures and stay at the right consistency, or they can't go to higher temperatures and be at the right consistency. So oil companies have developed something called multi-grade oils. Now the multi-grade oils allow us to have various temperatures from both low to high by adding something called a viscosity improver. And what that does is it allows the viscosity to change its viscosity at different temperatures, but not in the normal way. So normally, substances become less viscous as they get warmer and warmer, but when you have a viscosity improver added to the oil, it changes the shape of it and it changes the intermolecular forces to make it so that it becomes actually more viscous even though it's at a higher temperature. Let's look at an example of the SAE 0W30 that we have here. We can see that between -40 degrees Celsius and close to 0 degrees Celsius, it's going to behave with a 0W. That means the cold temperature viscosity will be around 0, which is very, very thin. Then we're going to go up to around 0 degrees Celsius up to about 35 degrees Celsius. It's going to behave like a 30 weight oil. And so we can see that that's the range that this operates in. This oil operates between -40 and 30 degrees Celsius, and it operates well, and it goes somewhere between 0 and 30 for its range. And generally speaking, what you will see for these ranges is that where you start and where you end will be approximately where you would start and end for the single grade oil. So in this case, the 0W started around -40 and it ended around 30 for the SAE 30. It ended around 35 degrees Celsius. If we look at the SAE 0W50, we can see that at -40 degrees Celsius it behaves like a 0W, just like the SAE 0W does, and then we can go all the way up to where we would expect to see for the 50 for the SAE 50. And so those patterns should follow in general where the information you have for the single grade oil will follow through for the multi-grade oil. The starting point and the ending point are more or less the same. Car manufacturers have adjusted their cars to specific grades of oil, so you need to make sure that you use whichever grade the oil cap on your car tells you to use. You don't want to change it up depending upon other things because those engines are set to a specific oil viscosity, allowing certain oils to pass through very small holes. If you use too thin, low viscosity oil, again, it won't lubricate enough, and if you use too high a viscosity oil, the oil won't get to the parts it needs to. It may clog certain holes, and again, the engine will not get lubricated and will be damaged. And this graphic basically shows us how the viscosity changes with temperature. So you can see the SAE 40 drops dramatically from a high viscosity to a low viscosity, and we can see that the SAE 15 follows basically the same line, where their viscosity is dropping as the temperature increases. And that's kind of what we expect to see for all oils. As the temperature increases, the viscosity will decrease. But notice that we don't see nearly the shift that you would in the multi-grade one. So the multi-grade one starts off close to where the SAE 15W is at 0 degrees Celsius, and then it drops down, but it only drops down to where the SAE 40 is at 100 degrees Celsius. And these measurements are generally made at 0 degrees Celsius, so we'll see that it's close to the 15W at 0 degrees Celsius, and it's close to the 40 at the higher temperature, 100 degrees Celsius. So the general range is 0 degrees Celsius to 100 degrees Celsius, and that's where they set those oil viscosity ratings. So the ones with the W are the cold temperature ones at 0 degrees Celsius. The ones without the W on them are at the higher temperature, 100 degrees Celsius, that most engines run at. This video gives you an idea of what those viscosities mean. So the first one is a 0W. The next one's a 5W30, and you can see it's much slower. Going from 0 to 5 has really slowed it down. Going up to 10, much slower. And we go up to 15, and then you'll see the 20, which we're not even going to see it really come out of the beaker because it's so much more viscous. And to get an idea of what these viscosity numbers that are given mean, we can see that water has a viscosity of 1 to 5. Blood or kerosene is somewhat more viscous, so blood is thicker than water, and it's around 10. And then you can go up to our motor oil of SAE of 10, which is very similar to corn syrup, around 50 to 100 centipoise, which is the measurement unit that they use. And we could go up to thicker oils like SAE 40 is like castor oil, a type of medicine, maybe similar to some medicines. And we can get higher and higher, and you can see down here at the bottom we have caulking compound, which does squeeze out of a tube and is a liquid, but it's hard to tell that it's a liquid. It's so thick. Anyway, that gives you some idea of what the numbers mean when we talk about what is viscosity and how slowly it will pour out of the container. You will not be tested on any of these parts of viscosity. You just need to know the definition. So you will not be asked anything about oils and their viscosity or how Heinz ketchup compares to an oil. So again, just to review, we're going to be talking about these 6 physical properties of liquids. The first one was evaporation, where we change a liquid into a gas at a temperature somewhere below the liquid's boiling point. That's when it's changing from a liquid to a gas, but it has to be below the boiling point. The vapor pressure is the measure of the tendency of a liquid to vaporize. It is dependent upon the interparticle forces. The weaker the forces, the higher the vapor pressure will be. Vapor pressure is also dependent upon temperature. So generally, the higher the temperature, the higher the vapor pressure will be. Then we can look at boiling point. This is the temperature at which the vapor pressure of a liquid is equal to the external pressure. When we talk about the normal boiling point of a liquid, we're talking about it at sea level or 1 atmosphere, but it does change dependent upon the elevation or the atmospheric pressure around it. So we talked about a pressure cooker changes the pressure, and so it has to get to a different number. And at the top of a mountain, remember, the higher the elevation, the lower the external pressure. That means the lower the boiling point. And then we can look at freezing point, and freezing point is the temperature at which a liquid becomes a solid. And again, notice that it says the freezing point. That's talking about the temperature where this occurs. The next one is surface tension, and that is how much a liquid likes to bead up because of the attractions of those particles to each other, especially to the particles in the center of the bead. When it's in contact with the air or gas, the gas does not have any attraction, so this has surface tension, which means it draws it towards it, and it is a force that is at the surface of any liquid. The last one was viscosity, which we talked a little more than you probably wanted to know, and it is a liquid's resistance to flow. Note that all of these are dependent upon the interparticle forces. So evaporation occurs faster with things that have weaker interparticle forces. The vapor pressure will be higher for substances that have weaker interparticle forces. The boiling point will be lower for substances that have weaker interparticle forces. The freezing point will be lower for substances that have weaker interparticle forces. It's harder for them to bond together. The surface tension will be lower for substances with weaker interparticle forces because they're not going to be holding together as tightly, and the viscosity will be lower for substances that have weaker interparticle particle forces because they will not be holding together as well either.